Welcome to a new video. In this video we will discuss the initial value and the final value theorem in the z domain using the z transform. We'll work out the calculations step by step and also verify these in MATLAB command window. Okay, we start with our theorems first. The initial value theorem, it is defined as if the time function x of t has a z transform, which is then given by the capital letter x of z, and that the limit of that function exists, so there must be some limit, must be converging, then the initial value, which is given by x of 0, of that function or that sequence given by these elements or notations, it can be calculated using this expression. That means the following: so the initial value of the time function is related to that limit z approaching infinity of that z transform of that function in the time domain. Okay, let's see an example in action that is more illustrative. For instance, we have this z transform of a function which was in a time domain, and we like to calculate the initial value of this expression in the z domain. So how do we do that? Well, now we look at our expression for our initial value, but first, in order to calculate this clearly, we need to first rewrite this as follows. So we rewrite our x of z by dividing the numerator and the denominator by z to the power 2, so z squared. The reason why I'm doing that is the following: because if I apply the formula here directly to this function, I get an infinite here, infinite there, and an infinite there. So I get this sort of infinite over infinite, which is undefined. And I need to really check that more clearly. So I divide everything here and there by z squared. So I get here z to the power minus 1. I get here 1 minus z to the power minus 1. And then you get here 1 minus e to the power minus 5t, z to the power minus 1. And t here is the sampling period, which is not defined in this case. So, and now if I look at this and apply this formula for my initial value, I can say then this formula can be then found by looking at the z to the power minus 1, because it is 1 over z, and 1 over z means 0. So this is 0. But this part is also 0, only this one. So we get here 1 minus 0 times 1 minus again 0. So it is not like 0 over 0 or infinite over 0, some kind of strange fraction. So we get here 0 over some number, which in this case 1 times 1. So this will approach to 0 over 1 times what I said, which is of course 0. So our final initial value here, our result is 0. We can also check this from the time domain function, because this z transform is from this time domain function, which is then 1 minus e to the power minus 5t, which is also recognized if you look at this in the z transform table. Now you can also look at this by substituting here for t is 0, which is time is equal to 0, which is the initial value. And when you do that, you get here 1 minus e to the power 0, because this will be 0 the time. So you get 1 minus 1, which is 0. So that is also proved here via the time domain. Let's also look at the final value theorem. Now that is defined as if, again, our time function has a z transform, the limit, this limit exists. In this case, the limit goes to 1. And all poles of that z transformed function lie inside the unit circle. It's like in the Laplace domain, we need to have all our poles in the left of plane. That is also the condition, similar condition here, but then we have a unit circle, which is our boundary, except for simple poles. So if you have a pole at 1, just one pole, by the way, at z is equal to 1, that is possible. Then the final value, which is then given by this expression of that function in the time or sequence, can be then calculated like so, or by this expression. So it doesn't matter which one you take. Okay, let's do that then. Let's do the right away, this on our same function. So the example is exact same. Now we will calculate the final value using this formula. So let's do that. So what you see is z minus 1 over z times our x of z. And you see here the z minus 1 over z minus 1 that cancels, and we have also the z over z that cancels. So we are left with this one. So limit of z approaching 1 of 1 minus e to the power minus 5 capital letter T over z minus e to the power minus 5 capital letter T. Now if I approach this to 1, so the z is approaching 1, this will be 1. This doesn't change the numerator. So I get here actually 1 minus e to the power minus 5 capital letter T divided by the same thing, which is 1. So it means I approach 1 as a final value. Can I also see that from the time domain? Of course, because this is my time domain representation, exact same function, of course. And we can look at our function when t approaches infinity. So that goes all the way to infinity. And that means if I let this approach infinity, that means e to the power minus 5t will be then 0, because this is a negative exponential. And we get here 1 minus 0, which is exactly 1. You can also calculate this in a different way if you prefer to have, let's say, negative exponents, like so. You can also use that, so by rewriting this as such, then we can use this for expression and then move on with the same format. So we can say, okay, now we would like to calculate the final value using this limit definition. Now you see directly 1 minus e to the power minus 1 here, and it will be cancelled by this expression. So you get actually this. What happens next? Now we need to substitute or let the z approach 1. That means this is then 1. That means 1 over 1 here. There is also 1 over 1 here. So I get exactly the same result as before, which is then 1 minus e to the power minus 5t over the same result. That is actually shown here, which is indeed, again, 1. So the time function will also give the same result. Okay. Let's see it also in MATLAB, and this is now our result from the previous discussion, the calculations. And how do we work this out in MATLAB? Now this is the command window script I have prepared for you here. You can define a variable in a z domain, which is then given by z is equal to tf, which is then called the transfer function. And here you give it like so. So this is then the z domain variable, and you define here some sampling period. It doesn't matter in this case, so you can also take it 1 or 0.001. So I took here 0.1 second. The x here is then expressed from our expression. So this is then the expression for our x in the z domain. This is also shown here, and if you want to really see it in the fractions, in the factorization form, I mean, then you can also use the ZPK model, which is then the zero pole gain model. And then you have it in a more convenient way, so you can look at it and recognize the poles and the zeros of your system. Then finally, we can make an impulse response to see that in a time domain. So what is really happening if this function is really starting at 0 and really approaching 1 as we have calculated. So let's do that. Now that's the next part, which is here our impulse response of this function x. Now what you see? Now we see here at the beginning that we start indeed at time is equal to 0 and our value is 0. So at time 0 the value is indeed 0. So initial value is 0, that's checked. And our final value, so approaching at some point, we approach, in this case it's 16 seconds, but you can also go to 20 seconds or 30 seconds, doesn't matter. It is approaching 1, so it is exactly 1 in this case. I have calculated 0, which is exact same as simulated. We have calculated the final value 1, which is also exact same as calculated. So this is also verified. Alright, it was our example considering the initial value and the final value of our z transformed function. We verified this also using the calculations, and now the MATLAB shows the same results. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.